Okay, so so today I'm gonna do this natural language processing course. I don't think I'm gonna do the other courses because they don't seem very interesting to me, to be honest. Maybe the advanced SQL, but yeah. So the next two courses I will do is probably natural language processing and intro to game AI and reinforcement learning. And this one is the one that I'm most curious about, to be honest. And I think I'm gonna divide this into two. If it's really 4 hours long, like it says there, because I've noticed that my attention starts to decline after 2 hours. And I'm also thinking about exploring the libraries on TensorFlow. TensorFlow. I figured out how to find out the uh, where the functions come from libraries and modules that you import. You can use I think it's inspect module, the name, and you can also use dir, and I think I'll show the file later that I wrote to find out the where the files come from. So I think I'll probably explore the TensorFlow library and Keras, which is part of TensorFlow, and explore how to build tensors before I continue to study the playlist on special relativity and tensors for beginners. But yeah, data comes in many different forms: timestamps, sensor readings, images, categorical labels, and such more, and so much more. But text is still some of the most valuable data out there for those who know how to use it. It's core about natural language processing. You use the leading NLP library, Spicy, Spacey, or something like that, to take on some of the most important tasks in working with text. By then, you'll be able to use Spacey for basic. I'm not sure if I'm saying this correctly, but whatever. Basic task processing, pattern matching, building machine learning models with text, representing text with word embeddings that numerically capture the meaning of words and documents. To get the most out of this course, you need some experience with machine learning. If you don't have experience with scikit-learn, check out Intro to Machine Learning, Intermediate Machine Learning, learn the fundamentals. NLP with Spacey. Spacey is the leading library for an NLP, and it has quickly become one of the most popular Python frameworks. Most people find it intuitive and has excellent documentation. Spacey relies on models that are language specific and come in different sizes. You can load Spacey model with spacey.load. Example here is how you would load the English language model. For Spacey, NLP equals space.load. Model loaded, you can process text like this. Doc equals NLP, T, something, what do you think? There's a lot you can do with the doc object you just created. Tokenizing. This returns a document object that contains tokens. A token is a unit of text in the document, such as individual words and punctuation. Space splits contractions like don't into two tokens, do and nt. You can see the tokens by iterating through the document. So each syllable probably is a token. Iterating through a document gives you token objects. Each of these tokens comes with additional information. In most cases, the important ones are token.lemma and token is stop. Text preprocessing. I think I'm gonna open the exercises right now, so I don't waste time waiting. There are a few types of preprocessing to improve how we model with words. The first is lemmatizing. The lemmas of a word is its base form. For example, walk is the lemma of the word walking. So when you lemmatize the word to walking, you would convert it to walk. It's also common to remove stop words. Stop words are words that occur frequently in the language and don't contain much information. English stop words include they, is, and, but, not. With a space token, token.lemma returns the lemma, while token.stop returns a boolean true if the token is a word stop word and false otherwise. I wonder how they categorize this. What's the process of categorization to find out this stuff? Why are lemmas and identify stop words important? Language data has a lot of noise mixing with informative content. The sentence above, the important words are tea, healthy, and calming. Removing stop words might help the predictive model focus on relevant words. Lemmatizing similarly helps by combining multiple forms of the same word into one base form. Calming calms calms, so I'll change the to calm. However, lemmatizing and dropping stop words might result in your model performing worse, so you should treat this preprocessing as part of your hyperparameter optimization process. Pattern matching. Another common NLP task is matching tokens or phrases within chunks of text or whole documents. You can do pattern matching with regular expressions, but spaces matching capabilities tend to be easier to use. To match individual tokens, you create a matcher. When you want to match a list of terms, it's easier and more efficient to use phrase matcher. For example, if you want to find where different smartphone models show up in some text, you can create patterns for the model names of interest. First, you create the phrase matcher itself. Just another library, apparently. The matcher is created by using the vocabulary of your model. Here we're using the small English model you loaded earlier. Setting attribute equals lower will match the phrases on lowercase text. This provides case insensitive matching. Next, you create a list of terms matching the text. The phrase matcher needs the patterns as documents objects. The easiest way to get this is with a list comprehension is the NLP model. Then you create a document from the text to search and use the phrase matcher to find where the terms occur in the text. The matches here are at the top of the match ID and the positions of the start and end of the phrase. I'm also wondering if that's how GPT-3 works, but I assume it works probably differently. I think it probably works by guessing the probability of the future words, what the future words would be, based on all its training, which is pretty much the whole data, the whole text from the internet. And I think it has around 2 billion parameters or something like that. So from what I understand, it works based on a context of some words, I think around 2,000 words. And then it tries to predict what the future text would be, what would make sense in that context. So it seems like it's complete. The business owner suggests use a diner reviews from the Yelp website to determine which dishes people liked and disliked. Put the data from Yelp. Before you get to analysis, run the code below to get a quick look at the data. They will also give you the list of menu items with common alternate spellings. So it has a text here. Review ID, business ID, date. Plan your analysis. In the data from Yelp and the list of menu items, do you have any ideas for how you could find which menu items have disappointed diners? Think about your answer, then run the sub below. So the first thing that comes to my mind is comparing the menu words with the text, trying to find good and bad words within the text context. So training a neural network on the text column to try to get a sense of the sentiment analysis of the text. Then I ask you to identify whether there are any foods on their menu that diners find disappointing. Yeah, so you get a general sentiment analysis of in the text, and then you compare that with the menu. That would be my guess. You could group reviews by what menu items they mention, and then calculate the average rating for reviews that mention each item. Tell which foods are mentioned in reviews with low scores, so the restaurant can fix the recipe or remove those foods from the menu. Find items in one review. You pursue this plan of calculating average scores of the reviews mentioning each menu item. It's the first step. You write code to extract the foods mentioned in a single review. Since menu items are multiple tokens alone, use a phrase matcher which can match a series of tokens. Fill in the files below to get a list of items matching a single menu item. So I have to use phrase matcher. Index of review, so 14. So this is getting the column text. And then this gets the index, gets the row of the column. And then I need to use phrase matcher to create a tokenized version of text to test on. Which I already forgot how to do. Add the item pattern to the matcher. Look at the docs for help with this step. So phrase matcher is probably the name of the object that I want to use. So I assume it's going to be something like this. And maybe, I think first I'm going to try to type it like this, and then I'm going to see on the tutorial if I got it correct or not. Which is the only thing I can think of without looking at the tutorial. So I'm pretty much saying apply this object on this test. But I'm not sure if this makes sense. Apparently here it's using phrase matcher, so it's probably not that. It's probably not what I need to do here. Create the rule-based phrase matcher setting a different attribute to match only will change the token attributes that will be compared to determine a match. By default, the incoming doc is checked for sequences of tokens the same RF value. Attributes the token attribute to match on. Defaults to RF the verbatim token. So maybe this is what I need to do. I think this only contains information for the last step. So I'm gonna have to look at the tutorial. So creates the NLP, then in the model loader you can process text like this. So it's gonna be doc. No, LMP. And then text true. Test. So it applies an LP to the text that is selected. Creates the phrase matcher. Create a list of tokens for each item in the menu. Add the item patterns to the matcher. So creating a tokenized version of the text you want to compare, then creating the phrase matcher. Then you need to create the tokenizer version of the menu because you want to compare both of them. And then here you compare. Just name for the set of rules we're matching to. So I'm gonna focus on this step first. So it has to apply NLP item for item in menu. This will apply this NLP. So from what I understand so far, the NLP is the method that you call to tokenize words. So here you want to apply this method to each word of the menu and put it on this list. So matcher.add. Just a name for the set of rules we're matching to. Now I don't understand really well. So here it already has the matcher.add. Find matches in the review doc. So I assume I need to add the token menu tokens list here. NLP menu tokens list. Because I want to add this to the matcher, which is created here. And then I want to compare this one with the reviews doc. Match is equal matcher dot matcher doc. So this is gonna be matcher, which has this object, reviews doc. And then it's gonna apply to the text that I'm trying to compare. So this is indented incorrectly. Now let's try again. Hopefully it works. Menu is not defined. So now I'm not sure if I should define it before. Maybe this step. I think this step is correct, but oh, I didn't run this cell. That's the problem. Because menu is supposed to be here. Let's see if this works now. Yeah. Now it's giving me a different problem. Argument string has incorrect type. Expected string got list. Line 25. So menu tokens list. So probably I need to erase this. So now self. I still this one. This one is wrong. So the issue is this expects a string and I'm passing in this list here. So I should probably do a loop, maybe. I'm not sure. Because I'm not sure if the method is supposed to add one by one or if I can add all of them at the same time. So I think I'm gonna do a loop, but doesn't seem like it's the correct thing to do. Let's see if this works. No, it still doesn't work. So I think I'm gonna look at the hints. It's in the review document to perform the matching. Yeah, I think I got the logic down, but it's just a problem of not knowing how to pass this menu token list one by one. This doesn't work. So I assume it has to be outside. But it's weird because of the way they did this. It feels like I should only change here. So it doesn't make sense to create the loop outside and then maybe that's the response they want. I'm gonna be right back. think what I'm going to do is try to do the loop outside, and then if it doesn't work, then I'm just gonna uh, see the solution. Yeah, it still doesn't work. Oh, so I'm not supposed to apply the NLP there. That was the issue. An integer is required. Oh, so where's the list? Now it's correct, maybe? Yeah, I think now it's correct. So when you're adding, you're not you're not using the NLP thing. You just use it on the text you're gonna test on. Because it's already applied here, I think. The matcher, so step 3. Matching on the whole dataset. Now run this matcher over the whole dataset and collect ratings for each menu item. Each review has a rating. Review.stars. Review.stars. For each item that appears in the review.text, append the review's rating to a list of ratings for that item. The lists are kept in a dictionary. To get the matched phrases, you can reference the phrase matcher documentation for the structure of each match object. List of match ID start and tuples describing the matches. A match tuple describes the span. Doc start end. Match ID is the ID of the added match pattern. Lectures import default dict. Item ratings is a dictionary of lists. If a key doesn't exist in item ratings, the key is added with an empty list as the value. For decks reviewing data iteros. So here's iterating over the rows of the data. The review is gonna be each column, each row. and the IDX is gonna be the index. I'm not sure if I understand completely what they want me to do. Run this matcher over the whole data set and collect ratings for each menu item. So the matcher is the matches. Each review has a rating, review.stars. For each item that appears in the review text, append the review's rating to a list ratings for that item. So I need to append to this item ratings. The lists are kept in a dictionary item ratings. So maybe it's matcher reviews dot text. So this is gonna apply the matcher using the matcher from the previous exercise. Now doc is gonna be reviews.text. It's gonna be matcher doc. Create a set of the items found in the review text. This is the part that I'm not sure about, I think. To get the match phrases, you can reference the phrase matcher documentation of each match object. List of match IDs, start and tuples describe the matches. A match tuple describes a span, doc, start, end. Match ID is the ID of the added match pattern. Create a set of the items found in the review text. Update item ratings with rating for each item found items. Transform the item strings to lowercase to make it case insensitive. I'm lost. I don't know. Because I already made the matcher here, the first line. So it can't be this line for the other ones. I just don't understand these instructions. Update item ratings with rating for each item in found items. Transform the item string to lowercase to make it in case. So here, suppose I need to append two item ratings in found items. But I'm not sure what the matcher doc returns. So matches is a list. So here saying match 1 equals to this number, but then I don't understand what this means. So maybe just the name of the word. The problem is that I don't understand what matches is very well. Just confusing as fuck. Match ID, start, end. So I assume it has ID, then start and end. Maybe it's just this. Set of items found in the review text. So I assume this is gonna give me this list here with the ID and the letters. Update item ratings with rating for each item in found items. Uh, let's try this if it works. Invalid syntax. Oh, it's because it's using this object notation because it's a string. So I should make the variables equal to this. Let's see if this works. Invalid syntax. So maybe if I put this inside of an object here. Yeah, I have no idea. No, I have to look at the hint. Returns a list of match ID, start, end. Tuples describing the matches. Match tuple describes the span. Doc start end. The match ID is the ID of the added match pattern. If S spans is set to true, a list of span objects is returned instead. So this is supposed to return a list with the ID and start end. Here is review here. Maybe that's what's wrong. Oh, so now is this part that is incorrect. Meshing can be called on doc or span only, got string. Oh, it's an LP. Name item ratings is not defined. Probably a typo. Clash.default dict object has no attribute append. So how do I append a dictionary? Maybe I have to use the add thing. It also has to be lowercase, I forgot about that. Transform the item strings to lowercase to make it okay. So I think it's gonna be this add matcher.add. Oh, but doesn't make sense because I already did the matches. So it doesn't make sense to add to the matcher. Just update instead. I think I did everything correct. Except the last part, maybe. Maybe I need to just update the whole thing. Oh, maybe that was incorrect. The issue is that I don't know what this thing is really. Yeah, I'm assuming that it is the words, like it says here. And the reviews, rating, to the items rating. Make sure to add the item string lowercase. I have no idea. Let's try this one. Yeah, I'm stuck. I don't know what to do. I think I probably have to look at the solution. If I do this, it will show up what it is. So it's just two words. It's because I'm doing one at a time. It's probably not gonna work. No. Interesting. I'm not, no, don't know. So this part I did correctly, I think. Matches true. No, wasn't using the set. I don't know what set does. Let's see. It makes it turns into an object. Term mathematics for sequence consisting of distinct language is also extended. This language by Python and can easily be made using SAT. Set method is used to convert any of the iterable to sequence of iterable elements with distinct elements. Turns an empty set if no element is passed. Yeah, creates an object, pretty much, I think. Yeah, turns either a tuple or a list. And I guess you have to do this because tuples are not, you can't change them. So you can't update the thing. Now reviews.stars, review.stars, I don't know why, how, where this came from and why is that. So it's looping through the found items. Yeah, I don't understand this at all, to be honest. Just stop printing this so it doesn't get really big. So found items is an object containing the words. Is looping through this object. Item rate is a dictionary list. If a key doesn't exist in item ratings, the key is added with an empty list of as the value. Yeah, I'm not sure if I really understand this. Be right back. The problem, the reason why I'm not understanding this really well is because I don't really get what each of these things are. These item ratings and found items as well. So I guess item ratings is a list, and then it's searching for, it's getting the value of the list from the words here on found items. And then it's appending a review.stars to that. But I just don't really understand what's going on. For some reason, it's very confusing to me. I guess it's appending the column. I think I gotta know. So each iteration is looping through this text. It's looping to the whole data, and then it's getting text. The evaluation of the sentiment analysis for the text column. And then, but the issue is, how is it possible that it's getting, because item ratings is supposed to be an empty list, dictionary of lists. The key doesn't exist in item ratings. The key is added with an empty list as the value. That's what I don't understand. There's a new dictionary like object. Default dict is a subclass of the built-in dict class. It overrides one method and adds one variable instance variable. The remaining functionality is the same as for dict class and is not documented here. Still don't get it. It's looping through the list, which is this object here with words, getting each word. Then it's searching for that word in the list. I guess it's just creating a key, which is items ratings item, and appending reviews star with that key. That's probably what's happening. So this here is just the value of the word from found items, and then appending the review dot stars to that word. I don't know. Not quite sure, but I think that's it. What's the worst reviewed item? Using this item ratings, find the menu item with the worst average rating. Calculate the mean ratings for each menu item as a dictionary. So it's gonna be item ratings item. It's gonna be pretty much the same loop, I think. Maybe not. Maybe just item ratings dot min. Thing is, I'm not sure how to get the min of dictionary. Find the worst item and write it as a string in worst item. This can be multiple lines of code if you want. So usually how I would do this is by comparing, creating a value variable, making it equal to a very small value, then comparing all the items to the variable, and if they are smaller, making the same. But here I'm not sure if that's what I'm supposed to do. Maybe I can use filter. JavaScript is the thing.filter, but Python I think is filter and then parentheses. Fuck you. The filter function, yeah. And but then, yeah, not sure how I would compare them. Sorted. It's a good way. So mean zip. Oh, almost 2 hours already. Still in the first one. So maybe it's mean the other way around. This. How can I make the number of iterations divided by length? This function is incorrect. I think I'm just gonna look at the thing. I think I'm spending too much time. Loop 3 item in item C, calculate the mean. The sum of the ratings divided by the number of ratings. This is easiest using dictionary comprehension. Then use the sorted function to sort dictionary keys based on the dictionary values. so frustrating. So the first one is wrong as well. And the idea is pretty much the same, but I was looking through the wrong thing and probably also doing the sum wrong, the wrong way. And then didn't know about this mean ratings.get function. Accounts important here. Similar to the mean ratings, you can calculate the number of reviews for each item. Here's the code. Should print the 10 best and 10 worst rated items. Look at the results and decide whether you think it's important to consider the number of reviews when interpreting scores of which items are best and worst. The less data you have true for any specific item, the less you can trust that the average rating is the real sentiment of the customers. This is fairly common sense. If more people tell you the same thing, you're more likely to believe it. It's also mathematically sound. As the number of data points increases, the error of the main decreases as 1 by the square root of that. Yeah, I wouldn't say that it's difficult. I just say that there's some, I lack some knowledge of the way that how to use these functions in Python. That's probably the reason why it's taking me so long to do this, because I'm not very familiar with sorted, .get, and the way to do these loops here. It's also very confusing to me to understand what is items ratings and the other things. Hopefully, yeah, I think with time it's gonna become easier to understand. Maybe I should search these functions. It's just part of the process. Maybe watching videos on that might help as well. When I come back, I'm gonna change the shirt I'm using. Task classification is spacey. Common task in NLP is task classification. This is classification in the conventional machine learning sense. It is applied to text. Examples include spam detection, sentiment analysis, and tagging customer queries. This tutorial will learn text classification space. The classifier will detect spam messages, common functionality in most email clients. Here's an overview of the data you will use. Bag of words. Machine learning models don't learn from the raw text data. Instead, you need to convert the text data to something numeric. Simplest common representation is a variation of one-hot encoding. It represents each document as a vector of term frequencies for each item in the vocabulary. The vocabulary is built from all the tokens, terms in the corpus, the collection of documents. As an example, take the sentences tea is life, tea is love, and tea is self, calming and delicious as our corpus. The vocabulary then is tea is life, blah, blah. So it's a dictionary of the words, not punctuation. For each document, count up how many times a term occurs and place the count in the appropriate element of a vector. The first sentence has t twice, that is the first position in our vocabulary. So we put the number 2 in the first element of the vector. Our sentence is, these vectors then look like. So version 1, version 2. This is called the bag of words representation. You can see that documents with similar terms will have similar vectors. Vocabularies frequently have tens of thousands of terms, so these vectors can be very large. Another common representation is TF-DF, term frequency inverse document frequency. TF-IDF is similar to bag of words, except that each term count is scaled by the term's frequency in the corpus. Using TF-IDF can potentially improve your models. You won't need it here, feel free to look it up though. Building a bag of words model. Once you have your documents in a bag of words representation, you can use those vectors as input to any machine learning model. Spacey handles the bag of words conversion and building a simple linear model for you with the text categorizer class. Text categorizer is a Spacey pipe. Pipes are classes for processing and transforming tokens. I'm going to create a Spacey model with NLP, Spacey.load, and Core Web SM. They are default pipes that perform parts of speech tagging, entity recognition, and other transformations. When you run text through a model doc, because NLP some text here, the output of the pipes are attached to the tokens in the doc object. Dilemmas for tokens.lemmas come from one of these pipes. You can remove or add pipes to models. What we'll do here is create an empty model without any pipes, other than a tokenizer. Since all models always have a tokenizer. Then we'll create a text categorizer pipe and add it to the empty model. Next, we'll add the labels to the model. Here, hammer for the real messages, spam messages. Training a text categorizer model. Next, we'll convert the labels in the data to the form text categorizer requires. For each document, you create a dictionary of Boolean values for each class. For example, if a text is Sam, we need a dictionary ham goes true, spam equals false. The model is looking for these labels inside another dictionary with the key cats. So spam text dot values. This part's a little bit confusing to me. Then I'll combine the text and labels into a single list. So each part of the list has the text and the labels. Now we're ready to train the model. First, create an optimizer using NLP.beginTraining. Space uses this optimizer to update the model. In general, it's more efficient to train models in small batches. Space provides the mini batch function that returns a generator yielding mini batches for training. Finally, the mini batches are split into text and labels, then used with NLP.update to update the model's parameters. So where is this train data coming from? Here. It's just confusing to understand this. Not sure if I'm the only one that has problem understanding this, but for some reason it's really confusing to me. More than the other ones were. For batch and batches. For text labels in batch. NLP.makeDocText. Not sure if makeDoc is a name of a library method or something. If they're declared somewhere. Doesn't look like it. This is just one training loop or epoch through the data. The model will typically need multiple epochs. Use another loop for more epochs and optionally reshuffle the training data in the beginning of each loop. Making predictions. Yeah. Now that you have a trained model, you can make predictions with the predict method. The input text needs to be tokenized with NLP.tokenizer. Then you pass the tokens to the predict method, which returns scores. The scores are the probability the input text belongs to the classes. Use text sketch to get to the score of each doc. The scores are used to predict a single class or label by choosing the label with the highest probability. Get the index of the highest probability with scores.argmax. Then use the index to get the label string from textcat.labels. I think I might stop here, come back to finish later. because I feel like this is gonna take me some time to finish the last part here. Such a great job for the Fox restaurant in the previous exercise that the chef has hired you for a new project. The restaurant menu includes an email address where visitors can give feedback about their food. The manager wants you to create a tool that automatically sends him all the negative reviews so he can fix them, while automatically sending all the positive reviews to the owner, so the manager can ask for a raise. You first build a model to distinguish positive reviews from negative reviews using Yelp reviews because these reviews include a rating with each review. The data consists of the text body of each review along with the star rating. Ratings with 1 2 stars count as negative, and ratings with 4 or 5 stars are positive. These 3 stars are neutral and have been dropped from the data. Evaluate the approach. Is there anything about this approach that concerns you? After you've thought about it, run the function below so see the point of view. Any way of setting up an ML problem will have multiple strengths and weaknesses. So you may have thought of different issues than listed here. The strength of this approach is that it allows you to distinguish positive emails, messages from negative emails, even though you don't have historical emails that you have labeled as positive or negative. The weakness of this approach is that the emails may be systematically different from Yelp reviews in ways that make your model less accurate. For example, customers might generally use different words or slang in emails. The model based on Yelp reviews won't have seen these words. If you wanted to see how serious the issue is, you could compare word frequencies between the two sources. In practice, manually reading a few emails from each source may be enough to see if it's a serious issue. If you wanted to do something fancier, you could create a dataset that contains both Yelp reviews and emails and see whether a model can tell a review's source from the text content. Ideally, you'd like to find that model didn't perform well because it would mean your data sources are similar. Your approach seems unnecessarily complex here. Review data and create a model. When you forward with your plan, you need to load the data. Here's some basic code to load the data and split it. So train data equals data.sample. It separates with 1 to 7 ratio, I think. Text equals train data.text values. It's going to be a string of the text on the train data. Labels equals positive O Y. For I, train data.sentiment.values. So did they show the data here? Oh. Split equals int length train data times split. Train labels equals cat labels for labels and labels split. Return text split train labels text split all labels. You use the training data to build a model. The code to build the model is the same as what you saw in the tutorial. That is copied below for you. First, run the cell below to look at a couple elements from your training data. So it's pretty much the review. Review and a category object with positive or negative values. But because your data is different, there are true lines in the modeling code that sell that true need to change. Can you figure out what they are? If you're not sure, take a second look at the data. Pay particular attention to the labels that should be fed to the text classifier. Modeling code cell that I need to change. So which one? This one or this? So it's probably the labels, I think. But I'm not sure. Maybe not because it's a different approach. Oh, so it is the labels. Train function. Implement a function training that updates a model with training data. Most of this is general data munging, which we filled in for you. Just add the one line of code necessary to update your model. So it already has the batch sizes. Train data is a list of tuples. Text label, text one, label one. For batching mini batch, train data size equals batch size. Split batch into text and labels, or text labels in batch. So each batch is at the tuple here. Doc equals nlp.makeDoc text. Example equals example dot from dict doc labels. Date model with text and labels. So model dot update maybe. No, it's this zip probably. NLP update. It's so confusing to me, I don't know why. So I did something wrong. I'm not sure what. If I do it like this, same shit. Maybe it's model.update instead of NLP. Nice. I think it worked. Maybe. Not sure. I'm not sure if I'm gonna watch videos about this later on because it's not really interesting to me. I mean, it is interesting, but it's not on top of my priority list to figure this out. I think there are other models that are more interesting, even though language is probably the main thing to solve a bunch of problems because everything can be viewed as language, which is just the connection of things. But it's not that I'm not that curious about building these types of models. Your loss isn't the same as our solution. Make sure to set batch size straight. So I did the model data update correctly. I'm not sure what's wrong here. Maybe it's just SGD optimizer. I'm not sure. I'm gonna look at the solution. Losses equals losses. I'm much more interested and curious about neural networks, about loss functions and that kind of stuff. Although it's pretty much the same thing here, but it's a different type of problem. I mean, I'm curious about understanding the behind the curtains process. I think that's more interesting to know. How are these models getting these conclusions? Wait for the cell to load. And this is the reason why I'm gonna look at the libraries for the things. Because even the book that I'm reading or the other resources online, I haven't seen too many videos or books talking about how to build the things from scratch. They just they mention it, the mathematics, but not in the code. In the code part, they just use the libraries. And to me, I think it's just a lot more interesting to understand how the models get to the conclusions instead of just being learning how to apply the models. I think because when you focus on how to apply the models, you're focusing on the effect, not the cause. I think the cause is much more interesting, which is the way to design these systems so that they understand how things work and what that says by the connection of things, how everything is connected, and how is that paradigm able to properly understand the connection between things. So instead of learning how how to build a model that classifies text and sentiment analysis, I'm more curious about why does that work, if that makes sense. Why the model time is over. That scared the shit out of me. I'm gonna go be right back. Yeah, this thing is still running. Maybe it broke or something, or just takes long time. Like most of the, not most, but some models do. Probabilities look reasonable. Now I should turn them into an actual prediction. Making predictions. Implement a function predict that predicts the sentiment of text examples. First, tokenize the text using an output tokenizer. Then pass those docs to the text categorizer, which you can get from an ap.getPipe. So I'm not sure if I'm supposed to do a list on the docs part. I think I'm supposed to do a list. That's docs. And here is a loop. So yeah, NOP tokenizer text. So I should do this loop here. For text. Then NLP.get pipe docs. Maybe it's text category instead of docs. Yeah. This text cat you get the scores for each doc. Maybe scores text cat equals that. Or it can be scores dot predict. Doesn't change much, I think, except for readability of the code. The issue now is that I'm gonna have to wait for this thing. Yeah, we should try to reload and see if it works. Can't run on the sauce. Maybe the issue is no Jupyter Notebook or Kaggle. Maybe this is running now. So Implement a function that evaluates a text categorizer model. This function evaluate takes a model along with text and labels. It returns the accuracy of the model, which is the number of correct predictions divided by all predictions. First, use predict methods you wrote earlier to get the predicted class for each text in tests. Then find where the predicted labels match the true gold standard labels and calculate the accuracy. Get predictions from text cat model using our predict method. So I'm not sure if I'm supposed to create a loop, but probably. I'll assume. Maybe not. Maybe I just call the method because inside the method is gonna loop already. So it's just gonna be predict models, predict text, model and text. This is gonna turn the prediction. Yeah, returns the scores. From labels, get the true class as a list of integers. +1, -0. So I should do a loop and then get the category values. When the scores, find the level with the highest score probability. I think I should do this loop on the other one. Boolean or int array indicating correct predictions. The accuracy number of correct predictions divided by all predictions. So this is gonna be a list. Correct predictions, I'm not sure. Apparently this is probably wrong there as well. I think I need to compare the predicted class with true class to get the correct predictions. but I'm not sure how to do that. Compare both. Number of correct predictions divided by, so this is going to be correct predictions divided by true class. No, divided by predict class. So I think this is to compare the true. Then here, correct predictions divided by predicted class. And how to compare the two, I'm not sure. Don't understand why this is taking so long. And this is where I stopped, I think. Maybe it just takes that long to train the model. Use a predict function to get the predict class. The labels look like cats, positive, true, negative, false. So this is the labels. You need to convert these into ones where positive is true and 0 where positive is false. So maybe it's not text cat. Yeah, because I did mine with scores. But the thing is, it's only assigned on the context of this function, so I don't think it should make a difference. So maybe I should use another variable there. Because either way, it's probably gonna be wrong if I use text cat. Once I have the predictions in true class, calculate the accuracy. I think this test cat should be this part here. So I get the values for each one. And I need to convert 2, 0, and 1. So it's a more complicated loop. Apparently this is not gonna, or either it's gonna take a bunch of time or it's not gonna finish. So I think I'm gonna jump to the next part. That's next tutorial. Word embeddings. You know at this point that machine learning on text requires that you first represent the text numerically. So far, we've done this with bag of words representations, but you can usually do better with words embedding. Word embeddings. Word embeddings, also called word vectors, represent each word numerically in such a way that vectors correspond to how that word is used or what it means. Vector encodings are learned by considering the context in which the words appear. Words that appear in similar contexts will have similar vectors. For example, vectors for leopard, lion, and tiger will be close together while they'll be far away from planet and castle. Even cooler relations between words can be examined with mathematical operations. Subtracting the vectors for man and woman will return another vector. If we add that to the vector for king, the result is close to the vector for queen. These vectors can be used as features for machine learning models. Word vectors will typically improve the performance of your models above bag of words encoding. Space provides embeddings learned from a model called Word2Vec. You can access them by loading a large language model like Encore Web LG. Then they will be available on tokens for the vector attributes. The thing I don't understand is how does it find the meaning? How does it figure out the connection? That's the thing. I don't think it's explained here. Represents each word numerically in such a way that vectors correspond to how the word is used or what it means. How does this happen? Vector encodings are learned by considering the context in which the words appear. Words that appear in similar contexts will have similar vectors. So it's pretty much making vectors based on the connection of the words from the text that is learning these connections from, which is very interesting. So this is pretty much implying that the meaning is equal or closely related to the distance of the use of words and their frequencies. So vocabulary in language is like a geometrical object, space-time. Which makes sense, makes a lot of sense. So I wonder if all languages have a relationship. Probably all languages have a relationship with mathematics. And the differentiation between them is the way that the geometrical structure is constructed from the framework of mathematics. It's kind of like mathematics is the US dollar for the market economy, whereas the common denominator from which everything, all the other coins are based on. Because language is just logic, and mathematics is, you can say that mathematics is the language of logic. So the variations of the language of logic are the different languages we have, which means that maybe you can create meaning by rearranging them in different ways, which creates different understanding of things. But then this brings the question of whether the model is learning the language or the structure behind the language. Like, is meaning the same as the structure or not? I guess you can say that it depends on the context, how big the database that makes up the context for the definition of the language, the vector space. The bigger the context, the closer the meaning it is to it. But then it becomes a problem of reference frame because each person is going to have a vastly different structure from which is observing that language. Yeah, I'm not really sure what to make of this. Because everyone has their own subjective experience of what a word means to them, which can be viewed as their belief structure, past experiences, which is another vector space from which that language is synchronizing itself with. And language could be viewed as the network that connects all these different perspectives into one thing. That's why everybody is able to understand each other, even though everybody has a different experience. These are 300-dimensional vectors with one vector for each word. However, we only have document level labels and our models won't be able to use the word level embeddings. So we need a vector representation for the entire document. There are many ways to combine all the word vectors into a single document vector we can use for model training. A simple and surprisingly effective approach is simply averaging the vectors for each word in the document. Then you can use this document's vectors for modeling. Spacie calculates the average document vector which you can get with dot vector. Here's an example loading the span data and converting each to document vectors. Classification models. The document vectors, you can train scikit-learn models, XGBoost models, or any other standard approach to modeling. Train scikit-learn, train test split, doc vectors, span.label, test size 0, 1, random state 0, random state 1. Here's an example using support vector machines. Scikit-learn provides an SVM classifier, linear SVC. This works similar to other scikit-learn models. So just creating the model and fitting to the training. Document similarity. Documents with similar content generally have similar vectors. So you can find similar documents by measuring the similarity between the vectors. Common metric for this is the cosine similarity, which measures the angle between two vectors A and B. This is the dot product of A and B divided by the magnitude of each vector. The cosine similarity can vary between -1 and 1, corresponding complete opposite to perfect similarity, respectively. To calculate it, you can use the metric from scikit-learn or write your own function. So I'm not sure you can say what I'm thinking about is whether or not, because it seems that what this model is doing is figuring out the relationship between like the vectorial space of words. I'm not sure you can say that the language and the words are the same thing. Like if the meaning behind them is this just the common denominator of all the all the meanings of everybody, and that's what language is. Words are just the average of the differences of vector spaces of each one's meaning space. So whatever the space is that everybody's intersects on is what defines language. I think that makes sense. But it might also be the case that even for human beings is not that well defined. Yeah, not sure. Where words are different than the meaning that they have. Because everyone has a unique meaning to every word. So the context is the approximation of the common meaning everyone has. But I'm not sure if that can be measured by the vector space of these words, or if it's a misrepresentation of what it actually is. And the reason why I think this matters is because you can make something that perfectly emulates language, but if it doesn't understand it, then it's probably going to be different in subtle ways. The applications of it. Uh, how did I ban? Vectorizing language. Embeddings are both conceptually clever and practically effective. Just write them for sentiment analysis model you built for the restaurant. Yeah, that's the thing. The other previous exercises from, not sure if it was from this course or the other ones, where it said that, I think it was from the ethics course, that you can have the language models that misrepresent the some words and categorize them the wrong way. I think this the reason that might be happening is because of this. Because the meaning they are giving is the approximation of the database of frequency of the words and not necessarily their meaning. Because meaning might be a deeper concept, which requires the fundamental knowledge of other aspects of life. Because language is attached to concept, and concept is a nested connection of ideas that go beyond language. I think that might be the problem here, a misrepresentation of these models in relationship to the language they're trying to emulate. But it's an interesting thing that even though we can have different languages, everybody seems to have very close meaning between what they mean by each word. Like the things and abstractions that words represent seem to have a common ground, even though the language changes. So there's probably a nested hierarchy of connections there that make up what the meaning of the language is, and how to accurately represent the context of it. That goes beyond just training the models based on the frequency of words and the vector space that they represent. The result is a matrix of 100 rows and 300 columns. Why 100 rows? Because we have one row for each column. And 300 columns, this is the same length as words vectors. See if you can figure out why document vectors and the same length as word vectors. Some knowledge of linear algebra or vector math would be needed to figure this out. Training a model on document vectors. See if this, apparently it ran here. Okay. Oh, it's another hour. Training a model document has. Next to train a linear SVC model using the document vectors. It runs pretty quick and works well in high dimensional settings like you have here. After running the linear SVC model, you might try experimenting with other types of models to see whether it improves your results. Model.fit. Next train. Y. Right? Let's see if that's correct. Yeah. Scratch space in case you want to experiment with other models. Document similarity for the same T-house review. Find the most similar reviews in the dataset using cosine similarity. Centering the vectors. Sometimes people center document vectors when calculating similarities. That is, they calculate the mean vector from all documents and they subtract this from each individual document's vector. Why do you think this could help with similarity metrics? Probably scale. Sometimes your document will already be fairly similar. For example, this dataset is all reviews of businesses. There will be strong similarities between the documents compared to new articles, technical manuals, and recipes. You end up with all the similarities between 0.8 and 1, no anti-similar documents. Similarity smaller than 0. The vectors are centered. You are comparing documents within your dataset as opposed to all possible documents. Find the most similar review. Given an example review below, find the most similar documents within the Yelp dataset using the cosine similarity. NP dot. So it's multiplying the vectors a and b divided by the square root of the a dot a. It's b dot b. Not sure what this does. No, it's the absolute value of a. Set the document vectors, calculate the mean for the vector. Should have shape 300. Subtract the mean from the vectors. Sum is this. Calculate similarities for each document in the dataset. Make sure to subtract the mean, the review vector. Get the index for the most similar document. So assume it's gonna be cosine. No, I'm not sure. Vec and centered. But that doesn't make sense. I'm not sure. I'm gonna look at the solution here. Get the correct mean vector. You need to set the access keywords. Argument should take the mean over the rows. The mean vector should be the same shape as the other document vectors, a trivial element vector. There you can iterate through each centered vector and calculate the cosine similarity with the T-House reviews vector. Finally, to get the index of the most similar review, the argmax method is useful. I'm not sure. Yeah, why not bird center here? Oh, it's not the same. Oops. Incorrect here. I think I'm gonna get the certificate for this one. Might come back some other time and do this again. Yeah, but I think this is it for this one. I'm not gonna get the certificate. But I think it was a good introduction to this concept. Later on, if I find some data set, there's some competition that requires this, I'm probably gonna come back to this and review these concepts based on what do I need to do. So I'm more motivated to do it. Because it's very frustrating to yeah. I'm gonna take a break for now. Let me see the courses here. And then I'm gonna start this intro to game AI reinforcement learning. And maybe look at the libraries, research the libraries and read the documentation. So see you. See you soon.